Triangular neighborhood networks are important because they have a very simple syntax, that is the triangle neighborhoods, and they're capable of change. The way change is accomplished is by edge rotation. So I've colored, this is the ground state in green, and I've colored two of the triangles in purple like this, and the two triangles share a common edge. What we'll do is we'll take, and you'll notice that all of the nodes in this structure have 6 edges coming into them. We'll take this edge out of this pair of nodes here and here, and we'll move the edge, rotate the edge so that it's now occupying these nodes. You'll notice that the ground state is completely flat. I mean, this is very important because as we generate defects by edge rotation, you'll see that the distortion to the ground state occurs. When edge rotation occurs in the ground state, there's an introduction of a significant distortion in the curvature of the ground state. As you can see now, we've rotated just one edge, but now the ground state's curvature is quite distorted. You'll also notice that I found a way of coloring the defects that make it easier to understand what's happening. The pink nodes are the 7-edge nodes. There are 2 of them now. And then there are 2 5-edge nodes. The 5-edge nodes are in light blue, but there's also an orange connector between each of the 5-edge nodes and the 7-edge nodes. So these 2 have an orange edge, these 2 have an orange edge, these 2, and the same with here. So in effect, there are 4 defects, or there are 4 possible ways that this structure could change. We could rotate this edge, which would have the effect of moving this defect here. But once you did that, well, then this edge would change from orange to green. In the same way, you could move this edge here, and the defect would move in this direction. But it's also possible you could move this edge here, and the defect would move in this direction, and then another one could move in this direction. So once you've made the first rotation, there are 4 defects that are possible. Our simulation program randomly chooses one of the edges to rotate and in effect move that defect away from where it was created. And then that leaves another defect which can also move away. Now I've moved both defects. They had been together here, and I've made 2 edge rotations that have the effect of moving the one defect along this channel. They're in the same channel, and then edge rotation that had the effect of moving this defect to here. So now you see there's green structure, which indicates all 6 edge nodes between the 2 defects, and they're moving independently. Whether a defect moves in this direction forward, let's say, or whether it moves in reverse is a matter of the context of signals in this environment here. The same thing is true here. Whether this moves forward in this direction or in reverse is a matter of, again, the local context of signals here. You'll notice still that the ground state is very distorted, but it's a local distortion. I mean, there's the connectivity of 6 edge nodes surrounding these local defects is still completely ground state-ish. And so it doesn't matter whether these defects are moving apart or whether they're moving together. If they're moving apart, we can consider this to be forward time. If they're moving together like this, then eventually they'll collide and they'll annihilate each other, which is just the reverse of the different actions that we've seen. So What we have here with edge rotation is the creation of defects and the movement of them away from each other, perhaps, or as defects move towards each other, they then collide in the same channel and annihilate each other. So this is a very primitive operator, creation, annihilation operator, which has a certain flavor of Feynman. And we'll show how different configurations have different effects. So what I've done now is I've put one defect in the middle of a ground state plane. Again, you can see the effect of the distortion to the ground state plane by having just one defect. It's very clear. Now, what I'll do in the next section is generate a defect here, let's say, and but not in the same channel. I mean, the channel in which this defect would move would be this channel right here. And so I'll generate a defect where there's a 5 and a 7. So I've added to the original defect that we have here a second defect. It had been launched. This defect is moving in this channel here. And I launched a defect that's moving in this channel here. If I rotate this edge here, that'll have the effect of moving this defect forward one notch. And if I rotate this edge here, this will have the effect of moving this defect in this direction. So now I've moved this defect from here up to here by an edge rotation. And so now the two defects have banged into each other. This defect was in this channel, and this defect was in this channel here moving. So now there's no edge that could be moved, that could be rotated, that would cause a 5-7 defect to move away. You can't move any of these edges that would so these 5-7s are defects, but they can no longer move forward. If this one was going this way and this one was going this way, they're blocked. And so the only thing that's possible is that you can take this edge here and re-rotate it, and that would have the effect of moving this defect in this way here. Or you can take this edge here, rotate it, and move this defect in that direction. So the conclusion is that when two defects meet each other in a right fashion, so that if this is the center and this is to the right of the center, then the effect is that the defects, the only thing they can do in terms of change is to move back in the way they came. So these are collisions that, instead of annihilating themselves when they're in the same, when the defects are in the same channel, in this case, defects that are right of each other have the effect of reversing the direction. And that's interesting, you know. I've now implemented a defect to the left of the central defect here, and it's moving in this direction. You can see that they haven't quite collided with each other at this point. So now I've moved this defect forward one edge rotation, and so now the two 7-edge nodes are adjacent to each other. And of course there's no edge here or over here that could be rotated that would take a defect away. So the only solution here, once again, is that the edge here should be rotated in which case this defect will move in this direction, and then the edge over here will be rotated, in which case the defect will move in that direction. So the generalization I think we can make here is that either the right or the left approaches in the same channel lead to the reversal of the direction of one or more of the defects. So this is, again, rather interesting property of the defect interaction. What we'll do next is to put a defect in one of the triangular channels here and see what happens there. So now I've launched the defect in this triangular channel. The 7-edge node is in pink and the 5-edge node is in blue. You see that this defect has not quite collided with this defect yet. So the next state will move it forward by moving this edge here, rotating that edge. So now I've advanced this defect in this triangular direction. And so a new phenomenon occurs. You see, for the first time now, there are 3 orange links, which means that this 5 is adjacent to this 7, this 5 is adjacent to this 7, and this 5 is adjacent to this 7, so that now we have 3 independent events that are possible. Before, when we had just 2 isolated defects, there were only 2 possibilities for action. But now we have 3. So we could rotate this edge here, which would have the effect of moving this defect in this direction. We could move this edge here, which would move this defect in this direction. But now, for the first time, we have this edge here, which can be rotated and would take this new defect in this direction. And so that's precisely what we're going to do. So now I've moved the defect that was here, the triple defect, in this direction. So now we see there's only one orange connector because this 5 and this 7 are adjacent to each other. But this 5 and this 7 are now isolated. And so as this defect moves off in this direction, these two, the 5 and the 7, are left abandoned in the ground state. And only if something comes along and bangs into them will they have any emotion in them. So this is very interesting because we did have 2 defects, one going in this direction and one going in this triangular direction here. Actually, it was coming in here. And because they banged into each other, now a 3rd defect formed, and it moved off, could move off independently, and in this direction. And so then these 2 nodes are left isolated. So there's curvature that's stuck in the middle of the ground state. And that's an interesting property. Well, we've been looking at the generation and motion of defects in the ground state, which consists of all 6-edge nodes. Here I've shown the ground state colored with one 6-edge node in orange. We could also look at structures where there's an isolated 5-edge node, and we could then study the interaction of defects either on the right or on the left with the 5-edge node. And the same thing is true for 7-edge nodes in the center. So here's a structure which has an isolated 7-edge node. We could also launch defects from the right or defects from the left at the 7-edge node and see what the interaction of the defect with the more single 7-edge node. But rather than using the knuffles as I've been doing, I've developed a method of diagrams that we'll follow in the next section. This is perhaps a way of summarizing how defects interact with themselves and with a variety of nodes, numbers. Of course, we could have 3, 4, and 8 and 9 edge structures, just like this 7 edge structure. So all of those interactions can be generalized rather well. I've developed a diagram that makes it possible to summarize how defects are created, how they move, and then how they annihilate themselves. This is a case where a single edge rotation produces a pair of defects, and they can either move apart, or if time is reversed, they can move together and annihilate themselves. This is a diagram that shows the interaction of two defects that are in adjacent channels. This channel is to the right of this channel. When the defects move together, they block each other. The only recourse then is for them to move in opposite directions. This diagram shows the motion of two defects in opposite channels, where this defect is in this channel and this is in the left channel. So now as this defect moves towards here, the two 7s will interact, and then there's no possibility of motion, continued motion. So then the defect would have to move back again, or this one could go back in that direction. The same way we can summarize the sections that we've seen before, where we have a defect in the one channel, and now on a triangular channel, the left approach, this defect moves towards this defect, and now the 5s and 7s will interact, and the result is that we have another defect possible, and then that defect will move away, leaving an isolated 7 and an isolated 5, and the defect will just move off by itself. So instead of showing you all of the completely rapid prototyping tool segments, we can now just use the diagrams to summarize the interaction of defects with, in this case, a 5-edge node. So this is a right approach, but as you see, as this defect moves towards the 5-edge node, the 5s will interact, and they'll block each other. So the only thing can happen is that the defect would move back again. On the other hand, if you have the left approach of a 5-7 defect to a 5-edge node, the 5s and 7s will interact, and at that point you'll have two defects possible. This was the original defect, and this is the new defect because this 7 and this 5 interact. So what can happen there is that the defect will move off by itself in this direction, and the 5-edge node will be left there by itself, isolated. So the net effect of this is that the 5-edge node has moved from here to here. Same sort of thing is true with the 7. Here's the interaction of a defect with a 7-edge node, and so what we see happens is that the 5 and the 7 interact, and this can be shown in this diagram here, where now there's a 5-7 interaction, and the net result of that is that the 5-7 defect moves off in this direction. The 7-edge node turns to a 6, and this 7 is left isolated by itself. So that's really interesting, and that sort of shows how defects created by edge rotation interact with each other and with nodes of various sizes. This section of the video uses a script generated for me by Daniel Rowe in the NIH. In the fabric of the icosahedron, there are signals flowing. You can't see the signals flowing. But when a signal, a certain pattern of signals is near a 5-edge node, the 5-edge nodes are shown in purple and the 6-edge nodes are shown in green. When a pair of signals are near a 5-edge node, then this triggers the formation of a defect by rotating an edge. Then the defects move away from each other in opposite directions along the channel where the defect was generated. I'm not showing the defect motion, and several stages of simulation occur between states that I'll show you. But what happens is that as the signals, the defects form, so for example here facing us is a defect that's formed in this first stage of simulation, and then in the next stage of simulation you see that there are several defects. There's a defect up on the top on the right, there's one in the center, and then there's one down on the left, and these defects move away from each other, so you can see them forming and moving because the defects are in purple, the 5s and the 7s. So the defects move and they will bump into each other and causing them to deflect on occasion with each other and at other times to leave nodes behind. In each stage of the simulation, the Amber script that Daniel Rowe has created will re-minimize the structure, and so the structure becomes gradually more distorted as more defects are created and as more 5 or edge nodes or 7 edge nodes are left abandoned in the structure. And so we see various states of deformation of the structure in time. And so this very nicely shows, first of all, the characteristics of the amber minimization, which keeps each of the edges both in the 6-edge nodes and the curved nodes, the 5s and the 7s. And so we see the structure becomes more and more distorted in time. And I'll just move the structure and show you its shape. Now, this algorithm that I'm using was only an experimental affair, and I might or have changed this, but this video, the object itself as it's distorting, shows very nicely how the defects form, how they interact with each other, how nodes are abandoned in various places, and then as a result how the structure deforms itself. So you see that now the structure, the fabric of the icosahedron is quite distorted, and we can just observe this state by state by state as it becomes more and more and more distorted. Now, I think the distortions are a function of the algorithm for the creation of the defect pairs by means of edge rotation. The portion about the aspects where the defects interact with each other, that seems to be properly resolved. But the question of how and when we the program generates defect pairs, that still seems to be up in the air somewhat. So I'll just cycle through. So the next state will bring us back. And so we'll just look at one view of the icosahedron and then cycle through the states of minimization. So this shows rather dramatically how edge rotation, defect pair creation, the motion of defects, the interaction of defects, how all of this works in a simple torus zero icosahedral structure.